If even the simplest form of life were discovered on Mars, it would actually be devastating news for humanity, and no news would be good news. This idea was proposed by Oxford philosopher Nick Bostrom. If life could emerge independently twice within the same solar system, yet we still find no trace of any advanced civilizations, that would mean nearly all civilizations get wiped out by some kind of great filter before reaching higher stages of development, and that would perfectly confirm how brutal the great filter really is. If the birth of life isn't rare, then the threshold that filters out civilizations might be extremely high, which in turn suggests how unbelievably rare it is for Earth to make it past all those barriers. This leads to another possibility. Life on Earth might be completely alone in the universe. Hello Earthlings, I'm Norian. Let's talk about the loneliest idea of all, the rare Earth hypothesis. Carl Sagan once said that astronomy is a humbling and character-shaping experience. So far, after decades of searching, we still haven't found a single confirmed radio signal proving the existence of extraterrestrial life. And among the thousands of exoplanets we've discovered, none has shown chemical signs indicating the presence of life. But numbers don't lie. The universe contains billions upon billions of stars, each possibly with its own planetary system. To say Earth is the only place with life in the entire universe feels completely illogical. Are the conditions for life really so harsh that Earth is the only place where life could survive long enough to evolve intelligence? That is the core of the rare Earth hypothesis. We all know how vast the universe is. With so many stars, even with incredibly low odds of life forming, there should theoretically still be countless civilizations out there, yet we've found nothing. Why is that? Fermi's famous question, "Where is everybody?" has turned into one of the biggest scientific mysteries of the past century, the Fermi paradox. People have come up with millions of explanations, from super predator civilizations wiping others out to the idea that we're locked inside some kind of galactic zoo. But if we're being serious, we have to consider the simplest answer. We haven't found aliens because they just don't exist. In astrobiology, we only have one data point: life on Earth. All life we know relies on DNA, carbon, and water. But the universe might host forms of life completely outside our definitions. Still, Earth biology is our only reference. Life on Earth actually appeared pretty quickly. Within a few 100 million years, single-celled organisms emerged. These were self-replicating organic machines. But they stayed that way for more than 2 billion years before eukaryotes finally appeared. Eukaryotes have specialized structures like nuclei and mitochondria, meaning single-celled life was becoming more complex, and that step alone took 2 billion years. Then, 600 million years ago, multicellular life emerged. In other words, for 87% of Earth's history, all life was just simple, single-celled organisms. It took 3.9 billion years before life made this leap. Then something strange happened. About 540 million years ago, just 60 million years after multicellular life appeared, the Cambrian explosion occurred. Hundreds of millions of species suddenly emerged in the oceans. Plants and animals appeared out of nowhere. Every plant and animal alive today can be traced back to those sudden early forms. Think about that. After nearly 4 billion years of quiet, life suddenly exploded. When people discuss the Great Filter, the leap from single-celled to multicellular organisms is undoubtedly one of the hardest filters to pass. How rare is that leap? How stable must a planet be to allow it after 4 billion years? This question made many scientists wonder, what if we really are alone? What if the conditions needed for intelligent life are so extreme that they happened only on Earth? If so, what exactly are those conditions? Back in 2000, Peter Ward and Donald Brownlee explored these ideas in their book, Rare Earth: Why Complex Life is Uncommon in the Universe. This theory became known as the Rare Earth hypothesis, and it lays out 5 core foundations plus 3 additional key conditions. 1. Our position in the Milky Way, the galactic habitable zone. We're all familiar with the habitable zone around a star, where liquid water can exist. But there may also be a galactic habitable zone, and we just happen to be in it. Many used to think life was more likely near the galactic center because of how active it is. But the problem is that activity comes with extreme radiation. Hubble images of the Andromeda Galaxy show that the center is a violent furnace of massive stars. Supernovas, hypernovas, gamma-ray bursts, and black holes. All this activity releases deadly radiation that would render nearby planets lifeless, with no such thing as nighttime. But we are far from the galactic center, situated between 2 spiral arms. We're far enough from chaotic starbirth regions but still receive enough heavy elements from past supernova explosions. And our local star density is low, reducing the chance that other stars might pass close enough to disrupt our orbit. If being in the galactic habitable zone is necessary for life, then most stars in the Milky Way are automatically ruled out. 2. The type of our star, a stable, G-type main sequence star. The Sun is a G2 main sequence star, meaning it's stable for billions of years. with just the right size and temperature for life. Larger, hotter stars have habitable zones but emit so much UV radiation that they could strip atmospheres away. Smaller red dwarfs require planets to be extremely close, causing tidal locking, not ideal for life. Even stars identical to the Sun have limitations. Stars are volatile in their early stages, then enter a long stable phase, and eventually expand into red giants. Only that long middle period is suitable for life, and luckily, it lasts billions of years. But once you exclude unstable regions, non-sun-like stars, and stars too young or too old, the number of potential life-hosting stars becomes very small. And this is just the beginning. 3. The structure of our solar system, a unique planetary layout. Even with the right star, you need the right planet in the habitable zone, a rocky planet. Our solar system has 4 rocky inner planets and 4 outer gas giants. We once thought this layout was normal, but when we began observing exoplanets, we realized most planetary systems don't look like ours at all. A study by Montreal's Lauren Weiss on 909 planets around 355 stars found that most planets in other systems are similar in size and evenly spaced. Our solar system is totally different, from tiny Mercury to Jupiter, which is 1,000 times more massive than Earth. The distances between planets grow almost exponentially. This strange size and spacing pattern makes our solar system an outlier. It forces us to rethink its formation and why it's so different from others. In fact, compared to other systems, ours looks like 2 systems in one. The inner and outer solar systems, and Earth just happens to sit in the perfect spot of the inner system's habitable zone. Could this unique layout be a key factor for life? Quite possibly. 4. Jupiter's protection, the solar system's vacuum cleaner. Space is full of asteroids, comets, and interstellar objects that could wipe out life on Earth. Thankfully, Jupiter acts like a giant cosmic vacuum cleaner, absorbing many of these threats. In 1994, comet Shoemaker-Levy 9 slammed into Jupiter, leaving Earth-sized scars. Another impact mark appeared in 2009. Studies show Jupiter gets hit 2,000 to 8,000 times more often than Earth. Without Jupiter, impacts like the one that killed the dinosaurs would be routine, resetting life over and over, preventing evolution. And Jupiter is just one of 4 gas giants forming layers of protection. 5. The role of the Moon, Earth's stabilizing partner. Ironically, the biggest impact in Earth's history, the one that formed the Moon, may have been the key to life's birth. The Moon is incredibly unique. It stabilizes Earth's axial tilt and creates tides, which may have been crucial for early life. Some theories say life began in tidal pools where organic compounds concentrated as water evaporated. But how rare is this? We've never seen another moon planet system like Earth. Some moons are bigger, but none have a size ratio anything like ours. The most accepted explanation, a Mars-ized protoplanet hit Earth at an angle, ejecting material that later formed the Moon. Evidence from lunar rock supports this, and it seems to have happened only once in our entire solar system. We still don't know whether similar moon-forming events are common around other stars. We only discovered the first exomoon in 2018, and it was a Neptune-sized moon orbiting a gas giant. 6. Other critical factors. A strong magnetic field. Earth is the only rocky planet in the solar system with a strong magnetic field, generated by its iron-nickel core. It shields us from deadly solar radiation. We don't know whether rocky planets around other stars have similar magnetic fields, but based on our solar system, it doesn't seem common. Plate tectonics. Earth is also the only planet with active plate tectonics. This allows heat and gases to be recycled, maintaining a thick atmosphere and fertile land. Mars, for example, has magma, but no tectonic shifting. Olympus Mons formed from magma repeatedly erupting in the same place. Earth's crust, however, is constantly renewed. A special primitive atmosphere. Earth's early atmosphere was toxic, filled with methane, sulfur, ammonia, carbon monoxide, even hydrochloric acid. Not exactly vacation-friendly, but this cocktail may have been perfect for life's first building blocks. Such chemical conditions might be extremely rare elsewhere. In short, intelligent life on Earth required a long chain of extremely specific conditions, many of which we take for granted but may be incredibly rare. These conditions might be so unique that they exist nowhere else in the universe, meaning we may truly be alone. It's a sobering thought, and we currently have no evidence to disprove it. Of course, not everyone agrees with the rare Earth hypothesis. Many critics say it's too human-centered. As I mentioned, we only have one example of life, Earth, so we might be looking for the wrong thing entirely. Life forms beyond our imagination may exist. Another possibility is that Earth itself is the oddball. Maybe we are the strange ones in the universe. For many people, the question still comes down to numbers. With so many stars in the universe, the odds of us being alone seem tiny. Just look at the famous Hubble Deep Field photo. Every bright spot is a galaxy, each with countless stars and planets. Even if the odds are microscopic odds in a massive universe still add up. To think the universe never produced life anywhere else might be naive. Maybe intelligent life isn't common. Maybe it appears briefly, like flickering lights across cosmic history, never overlapping. Earth took 4.6 billion years to produce us. Whether we can survive another billion years is anyone's guess. It's possible the universe has produced millions of intelligent civilizations, all now gone. That fits the Great Filter theory. Or maybe interstellar travel is simply impossible because distances are too vast. Or maybe galactic history is like a string of blinking lights. Civilizations appear at different times but never meet. That's why, if we ever discover microbes on another planet in our solar system, it would be both the greatest and the most paradoxical discovery in human history. It would prove life isn't unique to Earth, but also confirm Bostrom's fear. Life emerging isn't rare. What's truly rare is intelligent civilizations surviving the Great Filter. So, do you think Earth is the only survivor that made it through all the barriers? Feel free to share your cosmic thoughts in the comments.